Today, we're diving straight into a piece of tech that literally redefines how we see the building blocks of reality. I'm talking about the FESM, the Field Emission Scanning Electron Microscope. If you've ever found yourself staring at one of those impossibly crisp, 3D-looking images of a fly's eye or maybe the intricate molecular structure of a microchip, well, you've seen what this machine can do. We're going to break down exactly how it pulls off these breathtaking results, its massive advantages, and, of course, its mechanical drawbacks.
Just to wrap our heads around the sheer scale we're dealing with here, I want you to imagine taking an object and magnifying it 1,000,000 times its original size. Crazy, right? At that scale, the invisible suddenly becomes visible. Smooth surfaces look like jagged mountain ranges, and the fundamental structures of materials are just laid totally bare. The FESM doesn't just magnify things, it completely changes how we interact with the nanoscale, which is absolutely crucial for driving modern science forward. We're using this complete guide to map out the whole story. We've got the towering internal mechanics that make it all work, the world-changing advantages it gives us, and yeah, the strict operational limitations we have to deal with.
Here's our roadmap for today. 1. Seeing the invisible. 2. Anatomy of the FESEM. 3. Unmatched imaging advantages. 4. The hidden challenges. And 5. Real-world applications.
Section 1. Seeing the invisible, defining the FESEM.
So, let's strip away the massive outer casing and all those complex computer arrays for a second. What does this machine fundamentally do? Well, the FESM is a microscope, providing exceptional resolution and high magnification specifically for nanoscale surface characterization. It is the ultimate tool when you absolutely need superior imaging quality in research or industry. And remember, it doesn't look through things like a standard optical microscope. Instead, it scans the surface, giving us these incredibly detailed topographical maps of materials at the nano level.
Section 2. Anatomy of the FESE, Journey of the Electron.
Let's actually take a literal journey down the electron beam to see how this all comes together. Keep in mind, this entire process happens inside an ultra-high vacuum system. It kicks off at the very top with the Field Emission Electron Source, or FE gun, and the anode. These generate and accelerate our primary electrons. These electrons then shoot downward, passing right through a condenser lens that shapes the beam. Next up, they hit the scanning coils. These are super important because they perfectly direct and sweep the beam across our sample. The beam is then finally focused by the objective lens right before it smacks into the target down in the sample chamber. Finally, detectors, specifically secondary electron and backscattered electron detectors, catch all those signals bouncing off the sample to build the image on our monitors. It's honestly a masterclass in physics and engineering.
Section 3. Unmatched imaging advantages, the superpowers.
So how does that perfectly aligned electron beam translate into actual results? Well, we're talking about ultra-high resolutions of 1.5 nanometers or better. To put that into perspective, 1.5 nanometers lets us clearly visualize features that are essentially molecular in size. You can see things like clustered nanoparticles at a 20 nanometer scale, meaning scientists can observe the fundamental geometry of their work with just absolute crystal clarity.
But it's not just about resolution. The FESM is packed with other superpowers. It features low-voltage operation, which is a big deal because getting high-quality images at low voltages protects highly delicate samples from getting damaged. Add to that its remarkably large depth of field. This is exactly what gives FESM images that iconic 3D-like surface look, where both the high peaks and deep valleys of a sample are perfectly in focus. And driving the whole shebang is a bright, incredibly fine electron beam. Because the source is so bright and the beam is so tiny, we get those sharp, high-contrast images at magnification soaring up to 1,000,000 times.
It sounds almost like magic, right? A machine that lets you peer into the atomic building blocks of the universe without destroying what you're looking at. But, as always, when we hear about superpowers like this, we've got to pause and ask, with power this great, what is the catch?
Section 4. The hidden challenges, the kryptonite.
Operating an FESM is definitely not point and shoot. The biggest immediate hurdle is the strict vacuum requirement. The machine absolutely demands an ultra-high vacuum environment to protect that field emission source. Without it, the machine just doesn't work. On top of that, operators have to constantly battle beam instability. The source can experience beam current fluctuations over time, meaning it needs constant, careful maintenance. And even with that low-voltage mode we talked about, sensitive samples are still at risk. Delicate materials can easily get damaged or experience charging, which totally ruins the image. So operators often have to apply precise, time-consuming sample coatings, usually conductive metals, just so the sample survives the process.
And all of this brings us to a harsh reality. The financial and operational costs are daunting. When you stack an FESM up against conventional, older tungsten scanning electron microscopes, the equipment, installation, and maintenance costs are just significantly higher. You're paying a massive premium for that 1.5 nanometer precision. It requires dedicated facilities, highly specialized techs, and a huge budget just to keep the lights on and the machine running every day.
Section 5. Real-world applications where it shines.
So, knowing all those demanding limitations and sky-high costs, where does this massive investment actually pay off? Well, despite the hurdles, the FESEM is absolutely essential for cutting-edge fields. It's the total backbone of advanced research in nanotechnology, where seeing 1.5 nanometer detail isn't just nice to have, it's non-negotiable. Materials science and semiconductor analysis rely on it constantly to inspect microchips and novel compounds for the tiniest defects. In life sciences, it maps biological structures with that amazing 3D clarity. And for industrial quality control, it's what ensures the high-tech products we use every single day are manufactured flawlessly, literally down to the atomic level.
To wrap up our explainer today, I want to leave you with this. We've seen how the FESM takes an electron beam, focuses it through magnetic lenses in an ultra-high vacuum, and gives us the ultimate superpower to view the 3D microscopic world. So considering how much advanced medicine and technology rely on this visualization, what world-changing future breakthroughs, maybe a new cure or a revolutionary clean energy material, might be sitting inside a FESM sample chamber right now, just waiting to be seen?